Hello, welcome back to Math Olympian. Since the last time we were looking at the Collatz Conjecture video, I've created a few more variables and I've changed quite a bit about this graph. So this is the second version of the graph. Since the last time we met, we had done the Ulam number and the Devakra number, and I explained how the Devakra number was converging between 0 and 2. Well, I've changed that entirely and I've redefined both of those things. So we got the peaks and troughs by doing the same Tigger process as what we needed to run the Collatz conjecture in the first place in the new set J. And then we have our BAT as our proportion number divided by our iterations. That's still the same. We have our dips as what we discussed last time, the length of S minus the length of J, and then subtract 1 because that's how many dips we actually had. And then for troughs, peaks, but the Devakra number, what we did is we took BAT number, and we divided it by the troughs, and we multiplied it by Ulam. And the reason we did that is because whenever you have a lower BAT number, you tend to have like a lower number of troughs compared to dips and stuff. And the Ulam number is just troughs over dips. So realistically, this would just cancel out and become BAT over dips because the troughs cancel out when you multiply the Ulam and the Devakra number. And when you do that, you basically cancel out the troughs, so you get BAT over dips. And when the BAT number is low, the dips number is usually high, so it will create a very small number. That's why we got something like 0.611 times 10 to the minus 5. There isn't really a reason for doing this way. It's just experimental. But I do see that it has a lot of flaws in the terms of it's not actually producing anything quite useful yet. Okay, and then I also made a new one, and that's Vermula, and that's because I wanted to have an addition of the Ulam instead of a multiplication, so then we didn't cancel out the troughs. So when the BAT number is large, the troughs is usually lower, so we can just divide it by the troughs, and then we can add the Ulam, because the Ulam will always be, it'll always have like at least one decimal place usually, like in the unit section, in the 10th section. So then I just averaged the two. I added the Vermula and Devakra, then divided by 4, and then I multiplied it by Ulam again. And that's because when you do that, you cancel out quite a few of the things, and you basically get, if you write this down, you get the max number plus the max number of the dips over iterations times the dips times the troughs, and it cancelled down quite nicely, and I'll show you that in another video. But the whole purpose of this program is not really to find a constant like I was mentioning before, but instead it's to, if I pick a number, for example, it's to tell me the nature of that number. So any power of 2, we have 0.75, we have 0.625, and if I pick something large like 0.1024, we have 0.525, and then something even larger, probably 2048. We can see that it's converging on 0.5. So if a number is a power of 2, a large power of 2, so let's say 2 to the power of 20, it is very close to 0.5. So if I make that 201, 202, something that works probably, we have 0.51. So it is converging on 0.5, or at least 0.51. Let's say instead that I have a number that is something that comes just before a power of 2, so 5, for example, it converges on 1. So if I pick 2 to the 20 minus 1, all divided by 3, so when we apply the Collatz conjecture, we multiply by 3 and add 1, we get a power of 2. Divide. Yeah. If we do that, then we get basically 349,525, and we converge on 1. Look how close it's getting to 1. But for any other number, so if we just pick a random number, like just a really long number, it tends to converge on 0.25. Now, I realize the reason it's doing that is probably because of my average here. I have a over 4 here, and that's what's causing the actual 0.25. So these terms must cancel and give something plus 1 over 4, right? And that something, as n, which is our number that we're iterating, tends to infinity, will tend to 0. So that might be a useful result that we'll look at in a different video when we properly analyze this particular graph. Anyways, so that's what I did with this graph. It helps you identify the type of number. So most numbers will converge on 0.25, and there's special numbers or powers of 2 and stuff. Like, let's try an odd power of 2, like a 2 to the power of 23. We'll still get close to 0.51 or 0.5. So that was our what we did since then. But yesterday I was looking at something different regarding the graph, and the issue I had with the bat constant in the other graphs is that the bat constant would get very small and slowly become insignificant as we tended end towards infinity. So instead I defined the bat constant slightly differently. I did the number of dips we have minus the number of peaks, which would always be a significantly large number, and then I divided that by the iterations, because it seemed to me that the larger the number of iterations there were, it seemed that the difference between the dips and the peaks was also larger. So that would give us something that is much close to a constant, and that gives us, in this case, for this number here, a ridiculously large number, is 0.386138613861, which is strange because it's a recurring number, and that was very unlikely that we would get one of those. Let's try a different number. We look at a different number. Our back constant is, with these large numbers, it takes ages for them just to iterate and to reach wherever we want them to reach. So we just need to be patient. So this one is 0.40054449. So this one isn't really repeating, but the one we had was quite interesting. Anyways, the dips is then the same as before. The peaks is the same as before. Everything's the same as before. Ulam is the same as before. It's the troughs over the dips. The reason we've done troughs over dips is because we basically want to know the proportion of the number of 3n plus 1s we have to the number of divided by 2s we have, and that's about 0.43. So then what I thought to do is, something useful I thought would be is to add the bat constant, the new bat constant, and the Ulam number, because when I added them, I was just experimenting. It seemed to always come out to be something familiar, like 0.832. So we can try that for smaller numbers as well. So we pick something like 1729. We are still going to get something around that area of 0.83. So for that number, we have an Ulam number of 0.52 and 0.307. If we pick a power of 2, like 0.2048, it's undefined, I'm pretty sure. No, it converges on 1, I think, because the Ulam number will basically be like, it'll basically be 0.1 almost, because what we're having when we have the Ulam number for peaks over troughs is that we have one trough, and that's the one here. So we're just doing the number of dips, which is 11, 1 over 11. So that's all we're getting from that. And we're just adding that to the bat constant. The bat constant for this will always be like 1. Any power of 2, the bat constant should be 1 using this system. So if I pick 2, that constant will be 1, and the Vermeulen number will be 2. So that's how I define the Vermeulen number. I've got another number, the Rashmi number. I haven't defined it yet, but one thing I was going to add is our old bat number. The reason I've changed it is because our old bat number used to be the same as this, except the dips and peaks weren't here. Instead, it was, I think it was the proportion number. It was the proportion number, and in this case, it's giving us the same thing. And the reason for that is because as we tend to infinity, the proportion number basically almost always becomes 1. Maybe that's because this calculator can't process it, but it does tend to 1, so it's not as important. We could actually just put what we had before here with the dips and peaks, and then we could also multiply by the proportion number, which is probably what I'm going to end up doing. This might change results, but we can check. No, it looks pretty constant still. I mean, that's because the proportion number is pretty normal. If we pick something like 1729, the proportion number is 3, and the back constant is 1.6, and that makes the Vermeulen number higher. So maybe that's something we can use, but at the same time, maybe it's not. Maybe it's not useful. But if we don't include the proportion number, then we were actually converging on 0.83, and that seems to be something that might be useful. So we've also got the Divarkar and Rashmi numbers to define. But what I'm thinking for the Divarkar number is we just do what we did for the bat number, but we add the proportion bit. So we'll do that, and we'll put this here. Perhaps we could average the two for the Vermeulen number. So if we take the bat number and we add it to this number here, and we divide the whole thing by 2, divide the whole thing by 2, we get 1.014, and that feels more regular. If I did this, for example, the Rashmi number would be 0.41 because the proportion number is 1, and we're just dividing it by 2. So that's quite simple, and that's what I've done so far. That's pretty interesting, and that's the new stuff we've done with the Collatz graph. And as you can see, it's really coming together now. I think we're coming closer to finding some sort of constant, and that could be the 0.83 that we're converging on, or possibly the new Rashmi number 0.46, because as we change the values, it's not exactly converging, but it is staying somewhere around the region of 0.3 and 0.4. So if we pick a different number, like something large like that, it'll get something around 0.4 or 0.3. So that's hopeful. Yeah, that's all I can think of to do with this graph here. So next video we'll be looking at using this for music, because I think we're spending too much time looking for constants and stuff, and I think if there's any more stuff regarding constants, I'll just add it to the paper rather than make a video about it. So thank you for watching. Please leave a like and subscribe. If you have any more questions about this graph and what I've been trying to do with it, please leave a comment where you ask me, and I will try and get back to you. Thank you again, and subscribe.